Properties of functions, chapter 2, section 3. Even functions. A function is even if for every number x in its domain, the number negative x is also in its domain, and f of negative x is equal to f of x. So if you plug x into the function and you plug negative x into the function, you get the same result. A function is odd if for every number x in its domain, the number negative x is also in its domain, and f of negative x is equal to the negative of f of x. So if you negate the input, it negates the output. Odd, even, and symmetry. A function is even if and only if its graph is symmetric with respect to the y-axis. Now, some of you may not be familiar with the term if and only if. Sometimes it's written as IFF. If and only if means that it works both ways. So it's basically saying a function is even if its graph is symmetric with respect to the y-axis, and a function's graph is symmetric with respect to the y-axis if it's even. So it has to be able to work both ways. A function is odd if and only if its graph is symmetric with respect to the origin. So even functions, the graph is symmetric with respect to the y-axis. Odd functions, the graph is symmetric with respect to the origin, and vice versa. If you have a graph that's symmetric with respect to the y-axis, it's an even function. If you have a graph that's symmetric with respect to the origin, it's an odd function. Odd, even, or neither. Let's look at this graph of a function. Well, looking at a graph, we've been told that if it's symmetric with respect to the y-axis, then it is an even function. If it's symmetric with respect to the origin, it's an odd function. And if neither one of those occurs, then it's neither even nor odd. In this case, we can see that if we were to fold this graph over the y-axis, it looks the same on both sides. So it's symmetric with respect to the y-axis, thus it's an even function. F of x equal to 3x. Well, if we plug in negative x in place of x, we get f of negative x is equal to 3 times negative x is equal to negative 3x. So if we negated the input x to make it negative x, we ended up negating the output 3x to make it negative 3x. So f of negative x is equal to negative f of x, thus an odd function. F of x is equal to 2x cubed minus 5. Plug in negative x in place of x, we get f of negative x is equal to 2 times negative x cubed minus 5, which gives us negative 2x cubed minus 5. That's not the original function f of x, and it's not the negation of the original function. So f of negative x is not equal to f of x. It's not equal to negative f of x. Therefore, it is neither odd nor even. Increasing functions. A function f is increasing on an open interval I if for any choice of x sub 1 and x sub 2 in I, with x sub 1 less than x sub 2, we have f of x sub 1 less than f of x sub 2. Basically saying if you take any two inputs and one of the inputs is smaller than the other input, then the associated outputs will have the same relation. So if your first input has a certain output and that first input is smaller than the second input, then your second output will be larger than your first input. Decreasing functions. A function is decreasing on an open interval I if for any choice of x sub 1 and x sub 2 in I, with x sub 1 less than x sub 2, we have f of x sub 1 greater than f of x sub 2. Saying the opposite, basically with the increasing function, we were basically saying as x increases, y increases. Now we're saying as x decreases, y increases, or you can look at it as x increases, y decreases. Constant functions. A function f is constant on an open interval I if for all choices of x and I, the value of f of x are equal. So it's constant if no matter what value you put in for x over some interval, the output f of x is the same. So let's look at a graph of a function and determine where it's increasing, decreasing, or constant. And we can see here this is definitely a function. It passes the vertical line test. So where is it increasing? Well, we see that from x equal to 0 to x equal to 2, y is increasing. So on the interval from 0 inclusive to 2 inclusive, y is increasing, so the function is increasing. We also see that from point C on, well, I guess it's from x equal to 5 to x equal to 8, it's also increasing. So we're increasing from 0 inclusive to 2 inclusive, united with 5 inclusive to 8 inclusive, so on those two intervals. It's decreasing on segment C, which is from x equal to 4 to x equal to 5 inclusive. And then it's constant on segment B, which is from x equal to 2 to x equal to 4. Local maximum. Let f be a function defined on some interval I. So we have a function that we're defining over some interval. A function f has a local maximum at C if there is an open interval in I containing C, so that for all x in this open interval, we have f of x less than or equal to f of c. We call f of c a local maximum value of f. What this is saying is, if there is some interval surrounding a point on the function that all of the values of the function surrounding this point are less than it, then we have a local maximum. Basically saying in that localized region, this is the highest point. A local minimum, let f be a function defined on some interval I. A function f has a local minimum at C if there is an open interval in I containing C, so that for all x in this open interval, we have f of x greater than or equal to f of c. We call f of c a local minimum value of f. So just the opposite, if you can create some interval around a point and all of the outputs or values of the function are greater than at that point, you have a local minimum. Basically, if you can see that that point is the lowest value in a region, then it's a local minimum. Absolute maximum, let f be a function defined on some interval I. If there is a number u in I for which f of x is less than or equal to f of u for all x in I, then f has an absolute maximum at u, and the number f of u is the absolute maximum of f on I. So this is taking that maximum thing even farther and saying, if there is a point on the function which is greater than all other points on the whole function over the interval, then that is an absolute maximum. It is the maximum value for the whole function, making the absolute maximum. Absolute minimum, the same idea. Let f be a function defined in some interval I. If there's a number v in I for which f of x is greater than or equal to f of v for all x in I, then f has an absolute minimum at v, and the number f of v is the absolute minimum of f and I. So again, that's just saying if there is some point on the function that is lower than all other points on the function, then that is an absolute minimum. It is the smallest value that the function gives. Now, the extreme values theorem says if f is a continuous function whose domain is a closed interval on the interval a to b inclusive, then f has an absolute maximum and an absolute minimum on that interval from a to b. So if you have a continuous function, which means it's not disjointed, it doesn't stop and start over some interval, then there's going to be an absolute maximum value and an absolute minimum value. So let's look for minima and maxima. Here we have our fuzzy graph again of a function, and we start looking for local maxima, and we see that the point -4,4 is the highest point in that area. We also see that the point 5,3 is surrounded by points that are lower than it. So the local maxima for this function are -4,4 and 5,3. Local minima, we see that the only point here that is surrounded by points larger than it, is we actually have two of them. At 2, -2, it's surrounded on both sides, but then we also have 6, 0, which has no points lower than it in its area. So we have local minima at 2, -2 and 6, 0. The absolute maximum is the highest point of the whole graph, and we see that occurs on the left-hand side at -4,4, and the absolute minimum obviously occurs at 2, -2, that being the lowest point on the graph. Now we're going to look at using a graphing utility to approximate local maxima and minima and to determine where a function is increasing or decreasing. Let's look at the function f of x is equal to x to the fourth minus 5x squared minus 3x plus 4. Now, that's not a quick, easy function to deal with, so that's where a graphing utility can come in handy. So I'm going to use Desmos.com. It's my graphing utility of choice, and it's basically an online graphing calculator. So here it is, a screenshot of me using Desmos.com. So you can see I've got f of x is equal to x to the fourth minus 5x squared minus 3x plus 4. And I took the liberty of not only plotting that, but also getting the points where there are maximums and minimums. So I've got those, and those of course are approximated values. So now I'm going to zoom in on that graph just a little bit so we can look at these and determine the local maxima, the local minima, and where the function is increasing, decreasing, or constant. So we can see here that the local maxima, there is one point that's a local maximum because it continues up forever. So we're talking over the full interval of this, which is the set of all real numbers. The local maxima that we can see here occurs at approximately -0.3, 4.5. Local minima, we see that there are two of them at -1.4, 2.2, and 1.7, -7.2. Well, where is it increasing, decreasing, or constant? Well, we can see that it's increasing from -4, x equal to -1.4 to -0.3. It's also increasing from 1.7 to infinity. It's decreasing from -infinity to -1.4 and from -0.3 to 1.7. And there is nowhere that it is constant on here. It does not remain constant anywhere through this graph. Average rate of change. If a and b, where a is not equal to b, are in the domain of a function y equals f of x, the average rate of change of f from a to b is defined as average rate of change is equal to the change in y or the change in x. Remember, delta y, the change in, delta x, the change in. Sounds like slope, doesn't it? Change in y over change in x, rise over run, is equal to f of b minus f of a over b minus a. So the output at B, the point B, minus the output at point A over B minus A. Of course, where A is not equal to B, because if they're equal, then you end up with a 0 in the denominator and we can't divide by 0. So you're basically finding the slope, but since we're doing it of a function that may not be a straight line, we call it the average rate of change. So over the distance between x equal to A and x equal to B, this is the average rate of change. It's how fast it's doing it on average. So let's take a look at that. F of x is equal to 2x cubed. Find the average rate of change over the interval from 2 to 7 inclusive. So first we're going to plug in 2 into the function. So f of 2 is equal to 2 times 2 cubed, which is 16. Then we're going to plug 7 into the function. F of 7 is equal to 2 times 7 cubed, which is 686. We're then going to take f of 7 minus f of 2 over 7 minus 2. So 686 minus 16 over 7 minus 2, which is 670 divided by 5, or 134. So the average rate of change of this function over the interval from 2 to 7 is 134. Slope of the secant line. The average rate of change of function from A to B equals the slope of the secant line containing the 2 points A, f of A, and B, f of B on its graph. So let's find the equation of a secant line. If we're going to find the equation of a secant line, first we need its slope. The slope, m, slope of a secant, is equal to the average rate of change. We need a point on the line, A, f of A. We could use B, f of B. We can go either way. We just need a point on the line. And then point slope form, y minus y1 is equal to m times x minus x1. So let's put that to use. If we have the function f of x is equal to x squared minus 5x plus 1, and we want to find the equation of the secant line that passes through f of x at x equal to 3 and 8, then we first plug 3 into the function. F of 3 is equal to 9 minus 15 plus 1 is equal to negative 5. We plug 8 into the function. So f of 8 is equal to 64 minus 40 plus 1, which is equal to 25. Then we find the slope of that secant line. 25 minus negative 5 over 8 minus 3 is equal to 30 over 5, or 6. So we have a slope of 6. And we have the point 3, negative 5, right? When f of 3 was equal to negative 5. So if we plug that into the point slope form, we have y minus negative 5 is equal to 6 times x minus 3. But we could also use the other point. We have a second point, so we could use the point 825, and we get y minus 25 is equal to 6 times x minus 8. So we were able to find two different equations in the point slope form. If you want to on your own, you can go and then solve those equations for x and for y and put it into slope intercept form, and you will find that you come out with the exact same equation.